This lecture, we continue our study of polynomials, looking at the fundamental theorem of algebra and also at sign diagrams. The x-intercepts of the graph of a polynomial are called the zeros, or roots of the polynomial. They are the x values for which y is equal to 0. It is easy to create a polynomial with prescribed zeros. Suppose we wanted a polynomial with zeros at x equals minus 2, x equals 1, x equals 2, and x equals 4. Then just take something like x plus 2, which is 0 at x equals minus 2, multiply it times x minus 1, which is 0 when x is 1, times x minus 3, which is 0 when x is 3, times x minus 4, which is 0 when x is 4. If you multiply them together, then anytime you stick in one of those x values, it makes one of the terms 0. Since 0 times anything is 0, the y value will be 0. If we evaluate this function at minus 2, then the first term is 0, so the whole thing is 0. If we evaluate it at x equals 1, the second term is 0, and so on. Here's the graph. Notice that it does what it's supposed to. It crosses the x-axis at minus 2, 1, 3, and 4. One might observe that if we wanted 4 different zeros, such as minus 2, 1, 3, and 4, then the polynomial should have degree 4. There is a vague sense in which the number of zeros is the meaning of degree. We might hope that a polynomial of degree n has n zeros. This is almost true. We will elaborate on this more in a later lesson, but here is the first draft of the fundamental theorem of algebra. A polynomial of degree n has, at most, n zeros. We can often find n zeros if we're willing to count some zeros more than once. This polynomial, x to the fourth minus 4x squared plus 3, degree 4, factors into the quadratics x squared minus 1 and x squared minus 3. It has 4 zeros. The first quadratic, x squared minus 1, has zeros at minus 1 and 1, and the second quadratic, x squared minus 3, has zeros at minus root 3 and positive root 3. 4 zeros, and the degree is 4. But if we alter the polynomial a little, dropping the constant term, then we have this expression. And if we factor it, we discover that it factors into x times x minus 2 times x plus 2. It has zeros at 2 and minus 2 and 0. If you look at the expression at the end of the last equation, you'll see that x minus 0 occurs twice. The 0 at x equals 0 occurs 2 times, and so we're going to count that twice. And if we do that, if we think of the polynomial of degree 4 as having the root 0 twice, then the number of zeros is equal to the degree. This polynomial of degree 4 has 4 zeros. They are minus 2 and 2, 0, and 0. Here are the graphs of the first polynomial, which has 4 different zeros, and the second polynomial, which has 4 zeros, but one of those zeros occurs at x equals 0. At x equals 0 on the right, that root occurs twice. The polynomial comes up and kisses the x-axis before moving away. Let's find a polynomial of degree 3 with zeros 0, 1, and 3. That's easy to do. All polynomials are going to look like, that have those zeros, are going to look something like this. X times x minus 1 times x minus 3 times possibly something else. So one answer is simply x times x minus 1 times x minus 3. There's a nice polynomial with zeros 0, 1, and 3. Here's another problem. Give the polynomial of degree 3 with roots 0, 1, and 3 that goes through the point minus 116. As we said before, polynomials with roots 0, 1, and 3 should look something like this. And if it's a degree 3 polynomial, a will be some real number. We need to find a. We're told that when we plug in minus 1, we get 16. So plug in minus 1 to this expression, and we get minus 8a. That means that a should be minus 2. So there's my answer, minus 2 times x minus 1 times x minus 3. We solve for a. A convenient aid to graphing a polynomial is to locate the zeros of the polynomial and then draw a sign diagram. A sign diagram keeps up with the sign, plus or minus, of the polynomial in the regions between the zero. Consider the polynomial like that. This is a fourth degree polynomial. It has zeros at 1, minus 3, and 4. In order from smallest to largest, these zeros are minus 3, 1, and 4. The intermediate value theorem assures us that the only way the graph of the polynomial could cross the x-axis would be at a 0. So in each of the regions between the zeros, from minus infinity to minus 3, or from minus 3 to 1, or from 1 to 4, or from 4 to infinity, the polynomial does not touch the x-axis. It has a particular sign, either positive or negative. Again, there's my polynomial. Think of the zeros as fences. Cutting off x equals minus 3 is one fence, x equals 1 is another, x equals 4 is a third. They separate these four regions. So the sign diagram is going to look like this. Write down the zeros, minus 3, 1, and 4. Think of them as fences. To the left of x equals minus 3, test some value. We could test minus 4, for example. And if you work it out, we get the product of 5 negative numbers. So we have a negative number to the left of minus 3. Since the 5 minus sign will cancel in pairs, leaving one minus sign still there. To the left of minus 3, the function is negative. Now pick something between minus 3 and 1. Oh, 0 is a nice number to plug in. Plug in 0, see what you get. You get something positive. So place a plus sign between minus 3 and 1. Test something between 1 and 4. Get positive again. Test something to the right of 4, say something like x equals 5. Check out g of 5, and you'll notice it's negative, and so we put in a minus sign there. So there's the sign diagram in the middle of this picture, with the zeros minus 3, 1, and 4 below the line, separating signs minus, plus, plus, and minus. If I take the sign diagram, let's do it a little faster. There are my fences, there are my regions. I got a negative, positive, positive, negative. All of this is going to give us a clue to the graph of a polynomial. In that last line, g of x is negative in the last one, not positive. It's negative. This is an aid to graphing. Minus, plus, plus, minus. For this diagram, we know that as x approaches minus 3 from the left, the graph must rise up to the x-axis, go through the x-axis, become positive after that until it hits x equals 1, drop back to the x-axis, kiss it at x equals 1, and bounce back up, staying above the x-axis until x equals 4, where it passes through the x-axis and drops below. We're getting all of that out of the sign diagram, and that tells me the graph looks something like this. Let's finish our analysis of this polynomial. Here are some typical questions one might ask about g of x. Describe the end behavior. This is a fourth degree polynomial. The leading coefficient is negative. Minus x to the fourth has end behavior like that. Let's find the real zeros. Well, 1 is a 0 twice. Minus 3 and 4 each are zeros once. Notice we have 4 zeros and degree 4. Find the x-intercept. We'll plug in 0. You get 24. So the y-intercept. The y-intercept is 0, 24. Determine the maximal number of turning points of the graph. The graph has degree 4, so it probably has 3 turning points. Draw the sign diagram. We just did that. Draw the graph. There it is. Those are typical questions we might ask of a polynomial graph. In the next presentation, we explore the zeros of polynomials.